Okay, so question 55. Which of the following conformers has the highest energy? So there's a little bit of setup that we have to do for this problem. The first of which is we need to figure out axial, equatorial, and relative up or down. So the way that we did this in class is that we're going to have our chlorine and methyl, and these are going to be constant throughout the entire molecule. So the only thing that's different is where they're actually positioned. So first off, we need to figure out if this is up or down, or axial or equatorial. So this chlorine is obviously axial, and it seems to be pointing down. So this is axial, down. And this methyl group is also axial. You see how it's completely vertical. This is axial, and it's pointing up. So since these are both axial, one's pointing down, one's pointing up, these are going to be in a trans configuration. So this is trans. Same thing for here. Example B. Let's call this example B. This is example A. Um, we have axial down and axial down, so they're both pointing down, so these are going to be in a cis configuration. And this example C is going to have axial down for the chlorine and axial up for the methyl. So down and up, so this is trans just as in example A. So this is trans. Okay, so that's the first bit. The second bit is now we're going to try to redraw these molecules, where we're going to redraw them in terms of a Newman projection. So the way that I'm going to orient you guys is to have my eyeball pointing down this carbon 1 to carbon 2 bond for this first example. Okay, and this is going to stay the same for each of these examples, so I'm just going to keep this the same. We're going to have this eyeball right here, and it's going to be looking down this carbon 1 to carbon 2 bond right here. So let's go ahead and name this guy carbon 2. Okay, so we're going to keep it like that. So now let's put in some Newman projections. So these are my Newman projections, and so the bond that I'm going to use to look down is the first carbon. So this is carbon 1 right there, and carbon 2 is actually obstructed. It's behind carbon 1, but you can't see it because, again, you're looking along this carbon 1 to carbon 2 bond. Okay, so this is carbon 1, and carbon 2 is right behind it. So now let's go ahead and insert our chlorine. So the chlorine is, we know, axial down, so if we're looking at it at this perspective, chlorine is going to be down. And then if we wanted to, we can also insert another hydrogen in here just to make it explicit. And the way that we have ourselves oriented is, now the hydrogen is going to be on our right, and the rest of the molecule is going to be over here. So we're just going to kind of draw a little squiggly line. This doesn't really matter so much. And so now, if you look at carbon 2, again, carbon 2 is behind carbon 1. If chlorine is facing down, the methyl group is facing up. So we're going to have our methyl group up here. And if we wanted to, we can draw in another hydrogen. So this is our hydrogen in an equatorial down position. This other hydrogen right here was in an equatorial up position. So now we're going to have these two hydrogens in another Gauss kind of interaction. And the rest of the molecule from carbon 2 is going to be off to the side, so we're just going to draw another squiggly. This part doesn't really matter so much. Okay. So now the kind of interaction that we have here is a 180 degree or 180 degree anti-configuration. So we've talked about in class how anti is a relatively stable, or it's actually a quite stable interaction. So you have removed the chlorine atom from the methyl as pretty much as far away as you can get it. So there is no Gauss interaction going on here. There is no destabilizing, eclipsing interaction going on here. This is about as good as it gets for this kind of 1-2 configuration. Okay. So now let's do the exact same thing, and let's compare this to C. So again, C, we're going to be looking down this carbon 1 to carbon 2 bond. And let's go ahead and draw in all of our other atoms. So off of this carbon 1, we're going to have a hydrogen, and off of carbon 2, we're also going to have a hydrogen going up, and we're going to have another hydrogen coming down. Now this is really important, that if you have an axial going down in the first position, and you go one carbon over to the carbon 2, you're still going to have one group that's axial, one group that's equatorial. So here we have an axial down, so the next position must have an axial up. So this is the axial up position. And so if you look again on carbon 1, we have an equatorial up. So if we go one carbon over, if we have an equatorial up, the next position has to be an equatorial down. It is impossible to have an equatorial up followed by a subsequent equatorial up. So that's why you have to alternate these. So if you have an equatorial up, the next one is equatorial down, the next one's equatorial up, the next one's going to be equatorial down. Okay, and that's just more of a general rule to make sure you are aware of that. A big mistake people make is having two axial ups that are right beside each other, and that's just an impossible way to draw these molecules. So this is a very, very important point, is if you have an axial down, you must follow with an axial up, that must be followed with an axial down, that must be followed with an axial up. So again, it alternates. So in reality, it's pretty easy to draw these guys, as long as you make sure you alternate. Okay, but that's neither here nor there. It got off on a little tangent. So let's go ahead and draw our chlorine. So if we're looking at it from this angle, we're looking on carbon 1 to carbon 2. Again, this is our carbon 1. Chlorine's going to be pointing down. And in this orientation, the hydrogen's pointing off to the left, and the rest of the molecules pointing off to the right. Okay, so again, we're looking down this bond. The carbon behind carbon 1 is carbon 2, so it's obscured right here. But in this case, the hydrogen's pointing up, so this is going to be an axial. And then the hydrogen that's equatorial is now pointing down. Okay? And then again, we have the rest of the molecule. So comparing and contrasting A to C, A is a relatively, stable configuration. But since we're comparing apples to apples, we have two trans configurations, one on the left, one on the right. So we're not getting any kind of stabilization by putting the methyl group in a more stable equatorial position, which it would be. So we've talked about, or we will talk about, how equatorial positions are way more stable than axial positions. So we're keeping that constant. The thing that we have changed is this anti-configuration. So here in this example A, we have a relatively stable 180 anti between the chlorine and the methyl. But notice how in example C, that 180 anti is completely gone. So in this case, what we're comparing is a hydrogen and a chlorine, versus in this case we have a chlorine to a methyl. So if you had to make a choice, C is overall going to be more stable. A and B are, yes, very stable, but of the two, C is more stable-ier, okay, if that makes any sense. All right, so of the two, C is more stable. Okay, so now for this example B, this cis configuration, we've talked about, or again, we will talk about this extremely unstable situation where you have a 1,3 diaxial interaction between these two groups. Okay, so these are in a 1,3 diaxial interaction positioning, and this is going to be extremely unstable. So extreme instability in OCHEM is always associated with higher energy. So basically what this question is asking you is, if the highest energy compound, what is it? It's going to be the compound that's the least stable. Okay, so of these two, A and C are quite stable actually, but example B is extremely unstable because it's in this 1,3 diaxial interaction positioning. So this has a 1,3 diaxial interaction, and it's going to be extremely unstable. Okay, so you can prove this to yourself by drawing a little bit more complicated Newman projection that has two Newmans attached to each other, and we've probably done this in class, but if not, try to draw this guy with two Newman projections and try to convince yourself that it's extremely unstable. It's a little bit more difficult, but if you are interested in more of the why, this will help out with that. Okay, next question.